Hello, and welcome back to our series of talks about artificial color replacement. Today, we will visit the beverage industry, analyzing the opportunities and challenges that you could face when switching to natural sourced colors. We will take a look at some of the technical factors that affect the color selection process based on performance and stability. Then, we will examine some practical examples of color matching or substitution in soft drink prototypes. And finally, we will conclude with some tips and tricks to succeed in the transition to natural colors. Let's start with some technical considerations for color election based on performance and stability. As with any other food matrix, there are several factors that can influence how natural colors perform in beverages, such as the base ingredients, additional ingredients and additives included in the recipe, the temperature and duration of the thermal processing, any sort of light exposure, which is related to the use of clear versus opaque packaging, the color dosage rate, flavor expectations, and also of vital importance, the regulatory requirements, which will be driven by the final market of sale. Besides water, the drink's recipe may include several other substances in solution or dispersion, such as fruit or vegetable pulp, sugars, organic acids, fiber, vitamins, minerals, cloudifiers, stabilizers, and antioxidants. These substances can have an individual or additive impact on how the added color looks. Here, you can see two strawberry instant drinks with different usage rates of titanium dioxide, giving each beverage a different level of cloudiness. The original drinks were colored with a blend of FD&C red number 40 and FD&C yellow number 5. On the right side of each image, you can see the respective redesigned drinks that use natural colors that in this case are blends of Veggie Bright Black Carrot and curcumin, both in powder form. Cloudiness promotes light scattering with two main effects. First, the increased whitening visually dilutes the color, and second, not all the wavelengths of incident light are scattered equally, which affects the hue. As we notice here, the cloudier drink required 1.8 times more color usage to reach the same perceived intensity when compared to the clearer sample. And it was also necessary to increase the ratio of red to yellow pigments in the cloudier drink to compensate for the slight change of hue caused by the light scattering. The natural color selected must be able to overcome both factors, the visual dilution and hue shift, which entails adjusting the pigment blend and optimizing their usage rates. In many drinks, like juice-based beverages or protein drinks, there may be one or more ingredients with inherent colors. Sometimes, these colors contribute to the identity of the flavor intended, but sometimes they distort it and the overall effect needs to be corrected. This example shows an apple and kiwi juice-based drink, where kiwi is supposed to be the characteristic flavor. The original base contains a lot of apple juice and some cloudiness due to its pulp content. Therefore, it has an off-beige color that gets brownish after it is heat processed. In the image on the right, you can see the target color, which is a blend of a nature-identical beta-carotene that has a bit of a cloud in artificial FD&C blue number 1. So, our natural alternative must be able to get the right hue and intensity to compensate for the extra brown of the base. To achieve the match, we used one of our MCL natural beta-carotene emulsions and our Verifill copper chlorophyllin to get a super close match. Note that the target market for this product was a country where copper chlorophyllin is permitted. For the US market, where it is not permitted, you could test a natural acid-stable blue color like our Evergero Galderia as an alternative to the blue number 1. Chemical interactions are also something to consider. For example, ascorbic acid is known to have a protective effect over pigments like carotenoids and copper chlorophyllin. However, it can also have a detrimental impact on systems colored with anthocyanins. We can appreciate that in this example. In the left image, we have a model drink colored again with our Veggie Bright Black Carrot without ascorbic acid, while the image on the right shows significant fading with the addition of 600 ppm of ascorbic acid. It is important to be aware of the presence of added ascorbic acid, but also any ascorbic acid that could come from any fruit juice used in the base. Both contributions must be accounted for in order to make the correct decision on the color usage rate to employ. One of the most obvious chemical interactions that we can have in beverages is that of pH. Several natural colors can exchange protons with the media, causing different effects like precipitation, as happens with Norbixen, copper chlorophyllin, and carmine, or like in this case with anthocyanins, displacing the wavelength of maximum light absorption, which results in a hue shift. The pH of the system therefore conditions the color election, as some options would be better suited than others for the beverage's color design. For a raspberry soft drink that has a low pH, anthocyanins from purple sweet potato may be a great option, but for a strawberry instant milkshake dry mix, other sources of red, like carmine or beetroot red, would be more suitable. Heat processing parameters, like temperature and holding time, are also important when choosing a natural color for drinks, because some colors are not as heat stable as others. For example, red beet shows a significant degree of fading when heat is applied, as shown on the right side picture. Other colors are far more heat stable, like Emsil paprika, that is shown on the left side of the slide, especially with the addition of about 300 ppm of ascorbic acid that boosts the pigment stability. Keep in mind that for this scenario, we have to take into account not only how steep the heating curve is, but also the speed at which the drink is cooled. Just as some pigments are more heat stable than others, there is variability in their light sensitivity. Visible light and UV radiation break down key chemical bonds responsible for the selective light absorption. In that regard, the selection of a natural option to match an artificial color depends on the packaging format. Let us see the extreme case of FD&C yellow number 5 that is often used in soft drinks sold in glass or PET bottles. The closest natural match in terms of hue and vibrancy is curcumin, but we already know that it is extremely light sensitive and wouldn't be a suitable choice for this application. If you're looking for a similar shade with better light stability, you might choose safflower, only if your target market permits it. As an alternative, you can opt for certain selected beta-carotene emulsions that provide a clear golden cast, like we see here with this Emsil beta-carotene. It won't be identical in hue to yellow number 5, but it will be a valid option to communicate similar flavor expectations. The addition of ascorbic acid, that we mentioned a couple minutes ago, will increase light stability. In any case, frosted, amber, white, or green colored bottles, as well as large labels or shrink wrapping, can help protect colors from fading due to light exposure. Be mindful that any packaging design, be it the original format or any desired modification, is a key aspect of shelf life stability assessment in both accelerated and real-time models and will be considered by our color scientists when evaluating your project. Dosage rate is an easy and straightforward tool to gain flexibility on product design. You can play with the color intensities to modulate taste perception or to differentiate different lines of products, as seen in the black carrot and carotene examples shown here. You can simplify your color inventory and multiply your options by only playing with the dosage rates. This applies perfectly to projects where several artificial colors need to be replaced, because as you see here, the same natural color, like this black carrot concentrate, can be a good match for the pink of a red number 3, Comicene, where it's permitted, or even for the intense fire engine red of a red number 40. Each matching project is unique, but be mindful that light, less saturated colors may imply a more obvious color fading during shelf life, as compared to drinks with an initial higher usage rate of the same pigment, even with the same amount of effective color loss. As we can influence taste intensity with varying usage rates of colors, flavor identity is naturally correlated to the hue of the pigment or pigment blends utilized. Unless we are dealing with a fantasy flavor like Nebula, Mermaid, or Caribbean Beach, flavor expectations are dictated by the visual input of color, and sensory congruency is definitely a desirable feature. And that reminds us that artificial dyes are not always used as straight colors. Blends of artificials are widely used to achieve a variety of flavors within the same product line. We are certainly able to offer you similar flexibility when dealing with a replacement project. Now that we have reviewed the factors affecting the decision process to replace or provide natural alternatives for artificial colors, let's see some examples of this with our natural colors. The model beverages shown here has a typical parameter of pH between 3.0 and 4.5, acidified with citric acid, and solid adjusted to 10 Brix with sucrose. They are presented in two packaging formats, PET bottles and glass decanters, to appreciate the effect that shape and material have over the color appearance. These prototypes have not undergone any heat treatment. Therefore, this only has the purpose of showing our options, but process and shelf life stability must be assessed in commercial projects. Let's start with the pink shades. A popular pink is erythrosine, or red number 3. This color is rarely used in low pH soft drinks because it's not acid stable. You could find it nevertheless in protein-based drinks. So in this case, we decided to use an alternative drink model, a kefir shake with a pH of 4.5. Beetroot red and carmine are the most suitable replacements for this model, and the choice will depend on the labeling and cost and use required. Purple sweet potato gives a slightly more purplish hue, but the stability at this mild pH must be assessed. In this case, the color retention was acceptable after 15 days in the dark at refrigerated conditions. Translucent beverages using erythrosine at pH greater than 4.5, like some nata de coco drinks, could be replaced by carmine or reformulated with a lower pH, permitting the use of anthocyanin blends of a similar shade, like our dragonberry red blend. Beetroot red is also a good option, shade-wise and cost-wise, but given that it is unsuitable for high water activity systems, it would only be recommended for instant dry mixes. Now, let's move to the red shades. Here we have perhaps the most used artificial red color and the only FD&C red permitted nowadays in the US, red number 40 or Allura red. This popular color can be substituted by amaze orange red, deodorized radish, black carrot, amaze red, and blends of anthocyanins. Sensory effects like flavor and aroma will guide the source of choice. Now, an all-time favorite color for drinks, orange. The warm hue of sunset yellow, or yellow number 6, is matched here in a translucent drink with clear carotenoid emulsions like M-Seal paprika and M-Seal beta-carotene. Other options include carminic acid and blends of natural reds like a radish and a yellow like safflower. Carotenoid emulsion stability must be studied for the matrix, the process, and the packaging system to avoid defects like ringing or cap staining. Light stability of carotenoids is improved by the addition of ascorbic acid, as we mentioned previously. If the target drink colored with sunset yellow is cloudy in nature, as it tends to happen with citrus-flavored drinks, cloudy emulsions of beta-carotene or paprika can be considered. Another option is our Veggie Bright Orange Carrot Plus, a carrot juice concentrate, high in carotenes and stabilized for its use in beverages. Staying in the citrusy family, let's take a look at yellows. The striking yellow hue of tartrazine, or FD&C yellow number 5, is matched almost to perfection with a fluorescent yellow of turmeric. But if the beverage is exposed to light, it will not be an option, and you'll have to opt for more light-stable options like safflower or lutein emulsions wherever these are permitted. Beta-carotene clear emulsions are more golden yellow in hue, but these could represent a fair compromise when light stability is at play. And as is typical with carotenoids, 300 ppm of vitamin C can be added for best results. Let's go for the green shades now, which are a bit more complicated in the US than in other countries. Green blends comprised of tartrazine and brilliant blue can be replaced with customized combinations of Eversure Galderia blue, our acid-stable blue color, and turmeric if the packaging is protected from light. If the pH of the beverage is closer to 4.5 to 5.0, spirulina can be used as a source of blue. Copper chlorophyllin, where permitted, delivers a different but nice deep green that can also be color corrected with a bit of yellow if required to match the target beverage. Herbal shades of green can be obtained with the use of M-Seal beta-carotene emulsions as the source of yellow for green blends with natural blues. And speaking about blues, these colors have been increasingly popular in later years. Let's see our options. Among the suitable natural blue solutions to replace Brilliant Blue, or Blue Number 1, we can count Eversure Spirulina for pH values above 4.5, and of course, Eversure Galderia Extract, perfectly suitable for acidic drinks for pH levels of 3.0 and higher. Gardenia Blue and Genipan Glycine Blue have a deeper indigo shade and could be an interesting light and heat-stable alternative for the redesign of blue beverages. And let's end with purple shades. Purples from artificial colors currently allowed in the U.S. market are obtained through the blend of Red Number 40, Allura, and Blue Number 1, Brilliant Blue. The orangey shade of Red 40 plus the slight greenish cast of Blue Number 1 results in a deep grape hue. Here we have obtained good matches with blends of Eversure Galderia extracts and our fire truck colored Amaze Orange Red, and another acceptable alternative using the same source of blue and our deep and attractive Amaze Red. Other markets use other artificial colors to get purple hues. Here, we are matching a blend of Karmazine and Brilliant Blue for a fantasy-like violet color. A close color was obtained by using Eversure Galderia extract with a Veggie Bright Black Carrot. If the beverage has a pH close to 4.5, imagine a collagen-based instant powder. Spirulina could be used as a source of blue, and a suitable red option for the blend would include Beetroot Red and Carmine. Thank you for joining this webinar series on artificial color replacement in beverages. For more information on replacing artificial colors and other applications, be sure to check out the other videos in our webinar series. If you have any technical or commercial inquiries about our product portfolio and capabilities, you can reach out to us through the contact section on our webpage. Goodbye.